Welcome back to our Algebra 2 series, and today we're looking at an interesting consequence of certain types of functions. And here I have a picture of some things that happen with functions, and mathematically we could equate this to things in the kitchen, like say a microwave. And let's say that there was a microwave that was able to do things to like a typical microwave would. And here we have the microwaver. And if you put the carrot into the microwaver, it turns into something other than a carrot. It might turn into maybe some, I don't know, some very soft, mushy, carrot-like stuff. And here's the little greens there. And then what if we could have something that was the unmicrowaver? So you put that mush into the unmicrowaver, and it comes out to be exactly as it was when you put it in. Well, that's exactly what we have when we have functions where there is an f of x function and then what we call an inverse function, and we write it this way, inverse. So the little negative 1 power there is indicating that we're undoing what we do with any x value. So we put an x value into the function, then we put it back into the inverse function, and what comes back out is an x value. That's by definition what inverses do. They undo what the original function did. Well, here's an example of a function, and notice, first of all, this is a shapes function where A maps onto the triangle, B, C, and D map onto the circle, and E maps onto the square. And of course, this type of function is perfectly legitimate because we know that in any function, f of x, all x values must map onto exactly one y value. And so this is our domain over here, and every domain value maps directly onto each single range value. Now try to imagine for a moment that this was the microwaver and unmicrowaver. If I have a value like b that turns into a circle, and I have a c that turns into a circle, and I have a d that turns into a circle, when I try to undo this, this circle, it's going to be very difficult to determine which of the three values that the circle should turn into. Should it turn into B, C, or D? We don't know. And so in that case, this function is not considered to be one-to-one. In other words, it doesn't go both ways because the circle does not know which value to go back to, and so this one is not functional. In other words, the inverse of our little shape function is not going to be a function because when it goes back the other way, it is not unique. So that's what we have to watch out for. One-to-one functions have to have the arrows. So if we go back up to here, one-to-one functions have to have the arrows going to individual items in both directions. Let's move along here. In the first example, if this is the case, and I were to graph the function, and I can also graph its inverse. Now let me show you how that works. For example, if this is f of x, then we have to have a function that will undo what the 2x minus 1 does. So let's give this a try. 2x minus 1 obviously is a line, and it has an a y-intercept at -1, and it has a slope of 2. So I'll put in a second point here at 1, 1, and we'll draw the line. And I will finish this by um, labeling maybe one more point here, and that would be the point 2, 3. That's right here. So this is 2, 3. And this point over here is 1, 1. And this point is the point 0, -1. Going back over to our function here, if I plug these points in here, x and y, then I would see that 0 turned into -1, 1 turned into itself, and 2 turned into 3. Now that's for f of x. For the inverse function, we know that the y now turns into the x, and the x is going to go back to the y. So we should have this -1 turning into a 0, and a 1 turning into a 1, and a 3 turning into a 2. In other words, we're undoing what we did in f of x. Well, of course, these three points can now be plotted. -1, 0 is over here. 1, 1 is right on top of the other one, and 3, 2 is here. And notice that this line goes in this direction. This would be considered f inverse of x, where the original problem is there. So here we have the point 3, 2. And again, these are the opposite ordered pairs, negative 1, 0. And notice that 1, 1, since it has the same x and y value, it just stays right there. Well, one interesting consequence of inverse functions is that if we draw this line, I've not done this very accurately, but if we draw the line y equals x, we'll notice that these points are symmetrical or reflections of each other over the line y equals x. And anytime there's a point on the line, it will be on both the function and its inverse. We've done this without calculating the inverse. We've simply graphed the first function and then graphed the inverse. Let me move down to another one. I believe it's on the next page here. Here we go. We're going to graph this function and its inverse, x cubed plus 2. We know what x cubed looks like. That's this function that kind of comes up this way and down this way. We'll draw that, but we're going to move it up 2 units. So I won't draw the root graph. I'll just draw the final graph at 2. And then we've got a point up here at 3. This is at the point 1, comma 3. And then we have a point over here at negative 1, 1. And drawn in here carefully, this is our original function f of x. Of course, this is the point 1, 3. Using our concept of reflection over the y equals x line, which is here now, I see already that my graph has crossed the y equals x line down here. So that means my inverse function should do so as well. This point here, which is 0, 2, 0, 2, should transform to 2, 0. And this point, which is the point 1, 3, should transform to 3, 1. This is probably the most difficult. That's negative 1, 1. That'll transform over to 1, negative 1. So reversing the ordered pairs gives us 1, negative 1 here. It gives us 2, 0 here, and gives us 3, 1 over here. These are the opposite points. And of course, it should look like some sort of symmetry. It's kind of hard to tell sometimes how this should go, but this will go down this way, and then we'll come up this way. And it looks like here we have almost what would appear to be a giant squid. I call this my giant squid graph. This is 2, 0, and this is 3, 1. And this is representing f inverse. Of course, this one is 1, negative 1. So we label a few points there just to indicate where those are, and this is our original f function. Again, you notice what happens here is that these points are reflections of each other over the y equals x line. So that's what we do when we're looking for something to undo the other function. And in this case, we see that f inverse undoes what the original function did. I don't have an actual function for that. We'll do that next. So that's how we graph these guys, graph the function and its inverse on the same set of axes. Now the second part of this set or this video is calculating the inverse of the actual function. And there's a method that we use, and it's the same every time for a function. The first thing we would like to do is we would like to set y equal to the function. And then I use a little pig's tail to indicate that I am executing the inverse. So I'm going to reverse my x's and my y's. So this is going to be looking something like this. Now when I solve for y, this is kind of interesting. If I switch my x's and y's, which is what happens in an inverse, but I solve for y, I end up with x plus 2 is equal to 3y, or 1/3 quantity x plus 2 is equal to y. Oh, I forgot my parentheses there. Let me rewrite that. X plus 2 in parentheses equals 3. Oh, here we go again. Here, let's make that a y. There we go. Okay, so we have this new function, and we will call this f inverse. I'm going to distribute that 1/3. It's 1/3 x plus 2/3. And that is my inverse function. Now, the interesting thing about a composite function, we saw this right at the beginning. If the x value goes into f of x and then it goes into f inverse of x, my answer should yield x. Well, knowing that, I think I can do this entire composite by showing, and I believe in the directions it says, verify that the composite function yields x. So the composite would be f of f inverse, that's an of, f inverse of x, or you can do it the other way around. In this case, I'm going to do f inverse, which is this guy down here, and I'm going to plug this into the f function and verify that the answer does indeed come out to be x. So that would be, instead of f of x, it would be 3 times a blob minus 2. And the blob is this inverse function, 1/3 x plus 2/3. This is called verifying our inverse. Distributing the 3 inside, we get x plus 2, and then we bring down the minus 2, and by golly, there it is, x. So the composite does yield x in this case, and it should in all cases of inverses. So in other words, this, if you go way back to the beginning of the video, this is our microwaver, and this would be our unmicrowaver in the problem. And finally, let me move down to the bottom here and do one that's a little bit harder with g of x. I'll use the same properties. So y equals x plus 1 over 3x minus 2. The same procedure that I used in the last one. Set y equal to the function and then use my little pig's tail to change the x and the y's. But in this case, notice that it's a 3 y minus 2 at the bottom, and there's a y plus 1 in the top. So I have two y values. This is going to be tricky to do, but we have done this computation before. This is to solve for y. In the first case, I'm going to multiply across. That's going to be 3y minus 2 multiplied by the x. And then I will distribute the x. So 3x y minus 2x equals y plus 2. I have to get this y term together with this y term so that I can get the two y's together and factor out the y. And that is done in a step here, 3xy minus y, and take this 2x to the other side as a positive 2x. And now we can continue by factoring out the y. This gives us a 3x minus 1. Oh, I'm sorry, I made a little mistake here. Let me go back. I wrote y plus 2, but that should be a y plus 1 there, I see. So let me correct that. Yeah, that's going to be there. My fault. Let me just work this out. Sorry about that. That's a y plus 1 here, plus 1. This comes from the numerator right up here. And then this should be 2x plus a 1, and this should also still be a 1 over here. All right, so let me finish this out here. That should be a 1. Sorry about that. And dividing by the 3x minus 1. Y equals 2x plus 1 over 3x minus 1. This will be called our G inverse 2x plus 1 over 3x minus 1. Now in the next video, I will show how to verify this function, and then I will move on to a couple of interesting other types of functions. But for this video, that should be enough to get you started.